So again, from yesterday here, just remember that acids tend to have this hydrogen on the left-hand side. We name them like an ionic compound. We'll do a little lesson on that because we're AP, so we need to do that. But again, we're going to have like HCl, for example, would break up into this H plus and Cl minus. This is what's responsible for all acidic properties. Like, for example, pHs are less than 7, things like that, okay, which we're going to have a list of properties coming up here. But usually the H will be in the front like that. H2SO4, for example, okay. You know, even if we went to go name, yes, it's a bunch of nonmetals, but even if we went to go name that, it'd be pretty tough, right? Because we can't name 3 atoms. We don't know how to do that with molecular compounds, right? We just do 2, like carbon dioxide, for example, or like yesterday's quiz there, dinitrogen pentaoxide or something like that. So that'd be pretty tough because this is 3 atoms, so we're going to name it like an acid, basically, which would be hydrogen sulfate, all right? H1 plus, sulfate's a 2 minus, hydrogen nitrate. And then don't forget, there is some that look like this as well, yes? So if we see this COOH, that's actually a specific type of group that we call a carboxylic acid, which you'll learn in grade 12. That's organic chemistry stuff. And that COOH group is also tells you that basically it's going to be an acid probably, all right? Again, another way to write that, sometimes you'll just see hydrogen acetate like that because the H would be in front, but we put it at the back because that's how it connects together, basically, right? Those would be weak acids, by the way, all right? Yeah, it has to be COOH. No. Well, yes, the CH3C part, or the CH3 might be different. So I might see C6H5, COOH. Yeah. Okay, here's some properties of acids. Again, we'll take a look at these here. I'll let you copy them, and then we'll talk about them. Okay. Well, let's talk a little bit about properties of acids. First of all, let's go in order here, I guess. So let's just kind of talk about this. Acids are sour tasting. Obviously, we're not going to investigate this in the lab because if you do, we call this natural selection. Okay. So don't taste stuff in the lab. That's a bad decision. Okay, if I got to tell you that, I'd be surprised you're AP. Okay, I'd be surprised you're grade 10. Let's put it that way. Maybe like 10 months old, maybe. Okay, but we're not going to taste stuff in the lab, obviously. But we know that acids are sour tasting, like for example, lemon juice, vinegar. Right? If you have the hiccups, and you cannot get rid of them, 1 tablespoon of vinegar. Swear. Works every time, all the time, 60% of the time. Vinegar, tablespoon of vinegar works. Trust me. I'm not lying to you. I just put some on a spoon and just go. Don't dilute it or anything. Just it's great. It's great. It works all the time. I'm gonna get an email now. My teacher told me to eat vinegar, drink vinegar. That's what's gonna happen. Acid-base indicators are chemicals that are used to determine if a solution is an acid or a base by changing color. Let's see here. So that would be a litmus indicator. Litmus paper is an indicator, turns red in the presence of an acid. So make sure you have that in there, of course. So acids turn red, okay? A couple of ways to remember this are their acids are always red. So if you put red litmus paper, you guys have used litmus paper before. If you put red litmus paper, it stays red or look wet. If you put blue in, it turns to red, yes? So it's always red. Acids are always red. Easy way to remember this is bases are always blue, BB, right? So, all right, BB, acids have to be red then. Acids have a pH that's less than 7. It could be anything less than 7. So 6.9, for example, is less than 7. That'd be slightly acidic, okay? And all the way down to 0, and actually goes past 0 as well. So 6, 5, 4, 3, 2, 1, and anywhere in between. And it goes down to 0, -1, -2, -2, -3, I'm sure as well. Like I said, acids react with metals. So if we put a little strip of magnesium in or something like that, you're going to see a lot of reactivity. Okay, probably in the form of some bubbles and things like that. All right. And acids feel wet, and the reason we'll talk about that is what we'll talk about with bases. So if you do get acid on your fingers by chance on Friday, what do? You what? Lick it off. Yeah, natural selection right there. Right? Yeah, lick it off. Yeah. What do you do if you get acid on your fingers or your hand or something? You put it under water. Yes? You just rinse it off. Okay. Don't come to me and be like, I got acid on my hand. I got acid. You could just rinse it off because that's what I'm going to do, the same thing. So just put it under some water. That's all you can do. Okay. Dilute it, of course. All right. So those are for acids there. Okay. Questions, anyone? Yes? We got all that filled in there somewhere. Electroconductivity, did we? I don't think we said that, eh? No. Oh, there. Sorry, I missed it. Yeah, acids conduct electricity. They're really good conductors of electricity. That's why, for example, car batteries, or most batteries anyway, have not the little alkaline batteries like the AA's and stuff, but like car batteries or boat batteries or RV batteries, that's why they have acid in them, right? In fact, what kind of acid do they have in them? Paige, you know this. Why not? Eh? What? Leave the jokes to me, okay? That's not funny. Don't laugh. Hey, I'm the joke teller. Sydney? Serious? And aisle 3 wasn't funny with the cookies? Yes, Ty? No. Anybody? No? You don't know what kind of acid? Yeah. Yeah, what is it though? You don't know what we don't know? Oh, we used to know this stuff. Sulfuric acid. It's H2SO4. And lead plates. They tend to be a very good conductor between. That's why batteries are heavy, because they got lead plates in them. Yeah. Okay. Sure. Okay. Yeah. Yeah. Exactly. Yeah. 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 In a battery? Well, that would probably be more along. That's probably not so much the car ones. That's probably more the like the smaller ones, right? So it would be the metal. It'd be kind of like the lead in that case, because you still need that conductivity, and metals are good conductors. So that'd probably be part of that. And it's got like a paste in there or something like that. Okay. All right. Well, we're not going to do that. We already talked about this, recognizing acids by the formula, I guess. We did that. Yep. So we're good with that, I think. Bases. All right. And drop the bass. Boom, 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 boom. Rolling. I'm a 5.0. Rag top down so my hair can blow. Waving at all the girls as drive by. Hey, look, there goes a fly guy. Ice, ice, baby. Dun, 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 dun. Vanilla ice. Stop, collaborate, and listen. That's all I know. Okay. Bases. Here we go. Where are we with bases here? So at the very top here, according to the Arrhenius theory, a base is a substance that releases hydroxide ions when it's dissolved in water. So for example, sodium hydroxide would give me, and you're going to write this in right here, sodium ions and hydroxide ions in water. Okay. That's a process known as something called dissociation. And when we put sodium hydroxide in fact, if you look up sodium hydroxide, which we can do because we have a solubility chart, yes? If you look up sodium hydroxide, it breaks apart very easily, all right? And what happens is we get a lot of these hydroxide ions. So just like acids belong to H+, all the properties that go with that, bases have OH-, right? So this is the base right here. That is the base right there. That gives you the basic properties of science 10. No. Basic. Base. Base. All right. I'll give you another example here. If you put calcium hydroxide into solid, by the way, because it's an ionic compound, by the way, right? That's how we get the hydroxide. It's an ionic compound. If we put calcium hydroxide into water, we will get some calcium 2+ ions and actually 2 hydroxide ions. that doesn't make it any more powerful as a base. We just get hydroxide ions, and as a result, that would be a base as well. Okay, that process is something called dissociation for that ionic compound. It's an ionic compound, and it's got a metal, and then the non-metal, of course, is that hydroxide ion, this OH minus. That's responsible for bases. All right, good? Ask about. Mm-hmm. Well, calcium hydroxide is an ionic compound, right? So 2 plus 1 minus, swap and drop. Yeah. When you put this into water, the two ions will break apart. So water was polar, like from yesterday, it'll pull this ionic compound apart. We'll get calcium 2 plus ions. We'll get some hydroxide ions floating around in water. This hydroxide is what gives you base properties. Okay, just like the acid, when we pull the HCl apart, we get H plus ions. That's the acid. When we pull this one apart, we get OH minus ions. That's the base. Okay, so I'll give you base properties. All right. Is that okay? Any other questions? All right. Now, I don't know, what else do we need here? Obviously, we need to do some examples here. So strong bases contain hydroxide anion coupled with a metal cation. Examples include sodium hydroxide, lithium hydroxide, magnesium hydroxide. There are also many other kind of bases. For example, NH3 is also basic. All right. We'll get back to that for a second. But NH3 turns out to be a base as well. Now, NH3 doesn't have OH minus in it, right? I don't see any O's there for that matter, and we don't need to worry about it, but just know that NH3 is a weak base, okay? This is what you would smell in window cleaner or like Drano and stuff like that, is a weak base, okay? And that's what that's the properties of that, all right? Don't worry about that one too much. We're probably not going to worry about that. Properties of bases, I'll let you guys go ahead and copy. We're going to fill in that same chart there, of course. So go ahead and do that. So filling in the same chart here, of course, bases are bitter tasting. They're also sometimes, if you've ever had a Tums, for example, that's what a base is. Tums are kind of chalky, that kind of deal. So they're usually bitter tasting or chalky kind of thing. They feel slippery. So when you get a base on your fingers, that's why when we talked about the other one, acids feel wet, basically. It kind of seems like a silly thing to say, but it'll feel like water. You know, if you get acid on your hands, it'll feel like water, and then you'll feel burning. Yes, that's kind of the natural progression there. Bases are slippery. So the first thing you'll feel is like your fingers are really slippery. It's like you have oil on them. And then the second thing you're going to feel is the burning, okay, because they still burn. So that's the only difference. But they do feel slippery. And again, we're not going to test this in the lab because, again, natural selection. Okay, it's never funny the second time. Okay, bases turn litmus paper blue, so bases turn blue. Okay, with litmus paper, they have a pH that is more than 7, so could be 7.5 or 7.2, all the way up to 14. Could be higher, 15, 16. Okay, and they will conduct electricity because they have ions. Okay, there's always a metal, sodium hydroxide, barium hydroxide, lithium hydroxide. So they have positive, negative, positive, negative. They will conduct electricity as well. So bases and acids both should conduct electrical current. All right. The difference between a base and an acid, the biggest difference is probably what? pH, yes? Right? So that would be an easy way to tell. They will conduct electricity, and they do not react with metals. So if we put a strip of magnesium in there, for example, you're not going to see any reaction, or or a very, very quick reaction anyway. It might take some time, but it's not going to be immediate like it would be with an acid. All right. Okay. Recognizing bases by their formulas. Again, I think we talked about this already, but again, we always have this hydroxide ion is what you're looking for here. All right, somewhere in the formula, so that OH. This OH is different than that other one I talked about with the acids, right? Because remember, in the acids, we don't have any metals, right? Like HCl, H2SO4. We do have, for example, CH3COOH, but there was no metal to go with that, right? The metal is actually the H plus there, kind of thing, with that COH. This is OH minus. It has to have like sodium or potassium or lithium or barium or magnesium to go with that OH. Yep.
So if bases conduct electricity and don't react with metals, why would we use acids and batteries instead of bases?
I don't know. Yeah. Um, properties of water. Is that where we are? Well, an acid-base, it says here on your notes, an acid-base indicator is a chemical that is used to determine if a solution is an acid or a base by changing color. Water is a polar molecule, which means it has, of course, a partially positive end and a partially negative end. And you guys can go ahead and draw this. Well, I don't know. Yeah, go ahead and draw that in that space too, I think. So this would be your oxygen here. Okay, these are your hydrogens here. Partial negative, partial positive. So again, we talked about last day, this is, you know, we kind of have this kind of ends to the molecule. So they're not full enough to become full positive, full negative ions, but there is a little bit of a difference there. They're not sharing those electrons equally. Basically, there's a lopsidedness to this molecule, basically. All right. So we call these partials, these little delta symbols here, partial positive, partial negative for the oxygen, partial positives for the hydrogens. So they got a little bit of a charge on those ends there. It's not, again, it's not like being ionic. Okay, that's different. That's a full positive, full negative. That's where electrons have been transferred. That doesn't happen here. Okay. Water molecules are attracted to each other and can form hydrogen bonds. I think you need to draw that. So this is a hydrogen bond right here, is what we call this, hydrogen bond, between basically these two molecules. And I guess I'll talk about this right now, but hydrogen bonding can help explain many of the special properties of water, including its relatively high boiling point. And it's when we say relatively high boiling point, we're talking about 100 degrees Celsius because it's a molecular compound, okay? But that's pretty good for this compound actually, because if there was no such thing as this hydrogen bonding, it would actually boil at a lot lower temperature. Okay, this hydrogen bond turns out to be relatively strong for molecular compounds. It's probably the strongest type that we have. All right, including its relatively high surface tension, so that's why you see the bubbles on water kind of thing, and the ability of ice to float. All right, I'm just going to go to this page here and okay. Oh, yeah, that's what we're going to do. Oh, yeah, okay. I'll give you a few seconds here. We'll copy this. Is that okay for everyone? And then we'll show you just a few other things here. But like I said, we're going to go to lab and I'll show you that the water is polar. In fact, on Friday we'll kind of do that. Hopefully, I'll have time for that. Friday's going to be a little bit jam-packed, so just kind of be ready to go. And we'll talk a little bit more about that tomorrow. I'll put it in Google Classroom as well, and I'll kind of explain what we're doing here. We have a couple things to do today, and we have lots of time, so that's perfect. All right, good, yes. Yeah, so we'll do that. Water's amazing, physical states of water, just so you kind of know. Ice kind of locked in together here. You don't have to write this down, but ice is kind of locked in together, and that's how you can get, you know, basically ice. Liquids, you'll see that they're not all connected here. So some are, like there's a little bit of a bond there, basically, or a little bit of attraction between those two molecules. And there is here, for example, but you'll notice that there isn't here. Okay, there isn't an attraction here and there's an attraction there kind of thing. So we got some attractions, but not really enough to hold it together in solid form. So we get a liquid form. And here we have gas form where technically they're all separate from one another, yes. And that would be in gas form, of course. And how do we get these different forms? Well, these are states, right? Solid, liquid, gas. We give them energy. So if you're like, we go outside at minus 20 degrees Celsius, and then we turn on the propane stove, we're going to start moving these particles, right? They're going to start to move. They're going to start to move. We give them kinetic energy more and more, okay? and they start to move, and eventually what happens at zero is we break enough of those bonds between these molecules that now we only have some bonds attached, right? There, where's one? There, kind of thing. So we get some bonds that are attached, but not all of them at zero, okay? And as we start to give them more and more kinetic energy, we start to heat it up more and more, okay? We're gonna break more and more of those bonds. And as we break more and more of those bonds, when we get to 100-ish, okay? I mean, that's kind of simplistically putting it, but we're gonna get individual molecules of water, right? Because they have enough energy, those attractions, those molecules can't hold on to each other anymore. They're going too fast, right? And that's how we get gases, all right? Yeah, we'll talk about this in Unit 2, but of course, when we talk about plants and photosynthesis and all that, how does water get up to the leaves? Well, it comes in through the roots, yes? And how does it get up there? Well, one part is cohesion adhesion, right? Water sticks together, right? We talked about this yesterday. One water kind of pulls on another water, and then this water pulls on that, and et cetera, et cetera. We talk about cohesion adhesion, right? Which is really hydrogen bonding. Good? Yeah? Okay. Liquid assets, of course, make sure you drink lots of water. That's important. Or in my case, coffee. Just kidding. We're going to do a few things here. I think that's it. Yeah, we're good. Okay, we're going to do a few things. I do know why we don't use bases for batteries. Because bases are, which one's more dangerous to you, bases or acids? Bases. So we don't want to be playing around with bases. Conductivity with acids, by the way. So when we talk about lead and an acid, this is Chem 30, but a lot of difference in a lot of difference in electrical potential between the two. So because there's so much more, and you wouldn't get that with a base necessarily, smaller window of electrical potential, but you get a larger electrical potential with acids usually, specific acids too. And then when you use a metal like lead, you'll see there's a chart in Chem 30 that one's at the top and the other one's at the bottom kind of thing. So there's a much bigger electrical potential for that. Okay, maybe we'll record this, but I don't know if you know this, but pure water, H2O, okay, when you put it, when you have pure water, I mean, just like we call it distilled sometimes is what you'll hear, or basically distilled basically means we take all the minerals, all the metal ions out. If you went to the water fountain here and you drank out of that, it tastes funny, doesn't it? I don't know if you know that or not. To me, it tastes funny. That's because it's got some copper in there, maybe some iron, okay? But copper from the pipes and iron and things like that. And in fact, if you go to around here, you'd probably have some calcium. That's why we have water softeners, yes? Or maybe some of you do, I don't know. We have a water softener. You put salt in it, and it basically takes out the calcium and the harder metals. That's why you get that white, crusty stuff around the sink, yes? Like around the taps, because it's calcium buildup, yes? And you put CLR or whatever you want to do, but that's basically the idea. So there's calcium and there's zinc and there's probably some iron in there and there's copper. So when we talk about distilled water, we take those out, those ions out, okay? And a water softener is partly doing that as well. But when we talk about pure water, we talk about pure H2O. Pure water should not conduct electrical current because it's a molecular compound, yes? Right? So it should not conduct electrical current. Now, I'm going to tell you, when we go to the lab, it may conduct a little bit of electrical current because, first of all, our water is not pure. It's pretty good, but it's not perfect, okay? If your glassware is dirty, it's going to be conductive because who knows what's on there. And to top it all off, water actually has the unique ability to actually self-ionize. It's called auto-ionization of water. So what this happens is we actually do get a little bit of those two ions. Water is able to break up into that a little bit. Now, it may break up into those two ions, but notice I have a double arrow here, which means that this goes back and forth, yes? So they may break up into this ion and this ion, but they also may combine back together to make H2O, right? So if you do put a conductivity meter into pure water, it may be very slightly conductive. It might be enough to register like a 1 on our conductivity meter. So you got to keep that in mind. So they might all be conductive at a 1 tomorrow, or on Friday, I should say, but that doesn't mean that it's actually the substance we're dissolving that's going to be conductive. It just means that water maybe is conducting a little bit. Okay. What's this? We talked about it today, so you should know if you're paying attention. What is that? No, I know that. What's that responsible for? Acid. What's this responsible for, Ben? Base. Okay. So look, yeah, it breaks up. So when you drink water, you're actually drinking a little bit of acid, but exactly at the same time, a little bit of base to neutralize each other out. Yes? But it does have that ability. Because we use this as kind of our standard, like our kind of our golden thing here, this is how we get a pH of 7, basically. This is where you get the neutral thing from. That's where they got this little chart from. That's they do a little logarithmic formula, which you'll learn in Chem 20, and they get basically a pH of 7 from that. And then they said, okay, well, that's neutral. And anything above that would be a base, and anything below that would be an acid. And that's kind of what they came up with. Logarithmic scale, it's based on, it's kind of the opposite. So the more H pluses you have, the lower the pH goes, basically is how it works. And vice versa. The more OHs you have, the higher the pH goes. Okay, you'll learn that someday. That's not important. But that's kind of where it came from. Okay, water has that ability to basically at times break itself up into a little bit of H plus and a little bit of OH minus. All right? Because remember, water's polar. So water's pulling on these other water molecules, and at some point it might pull an H plus off, and another water might pull an OH minus away, right? Break it up, and then it'd come back together probably. So there is going to be a little bit of that going on, a little bit of that. All right. So that's important to remember as well. So when you add water to a battery, the only reason you're adding distilled water, it's not because, first of all, you got to make sure the plates are covered in there. So you're adding water to make sure the plates are covered, the lead plates are covered in there. If you added something else, it could react with the acid and have a bad reaction. It could react with the acid to form a solid in there, which you wouldn't want. And it could gum up the plates as well. That's why over time, batteries only last for so long. If you have a really good battery charger, they have this program called desulfation, something like that. And basically what that does is it kind of breaks, it takes all the gunk that's attached itself to the lead plates and it breaks it back down again. So you can kind of reverse it, but it takes a lot of energy for that. You got to have a good battery charger to do that. It's not, you can't just hook it up and like at 18 volts and like burn everything off kind of thing. That's dangerous, but yeah, that's why I put distilled water in pure water, just so that it doesn't react with anything else. You are technically diluting it a little bit, but that acid's pretty strong in there. So definitely, if you ever open those up, you should put goggles on for sure. And if you ever get that on your hands, which I have, you'll know right away because it's, like I said, it's fairly strong and it burns pretty quick. So you'll feel the tingling sensation for sure. All right, good. I think